Okay, good afternoon. My name's Colin. I'm today's speaker. I'm going to talk about s2n, which is short for signal to noise. And that's our TLS SSL encryption library that we released over a year ago now at AWS. We released it as an open source project on GitHub. The reason for the name is just a pun on encryption in general. Is about taking signals, like meaningful data that you can interpret, and making it look like noise. That's just the art of cryptography. And so that's where the name came from. Really, really simple. What you can expect from this is we're going to cover why we built s2n, what our motivations were, how it arose. In doing that, we're going to cover a little bit about the OpenSSL Heartbleed bug, do a little bit of a deep dive on that, understand how that bug arose, how we try to prevent similar bugs from arising. We're going to talk about how we then started the s2n project as an open source project at AWS, with some perspectives on how that works at Amazon Web Services. And then we're going to talk about how we develop and test signal to noise, and where we are now and what our future plans are. I think this is really interesting because it's a unique opportunity for us to give kind of a view of how development works inside AWS. s2n is run by a virtual team of developers from multiple services. So we've got developers from S3, CloudFront, Elastic Load Balancer, the AWS security team, the AWS cryptography team. All of these people are involved. Many of us have worked on multiple other Amazon Web Services. And so the development style and the practices that we have in this project are strong examples of how we develop software on a day-to-day basis at AWS. So it's an interesting view into that. I don't mean to imply that our way is the best way to develop software or that there's one good way to develop software. There's many valid cultures of software development. But this is a take on how we do it and how we handle the unique challenges of a project like signal to noise and shipped software. So that's what we're going to talk about. So we're going to start why we built s2n. And to start with that, we need to go back to what we did without it. So before we had s2n, we used and actually continue to use OpenSSL widely at AWS. It's a library that's been around a very long time now. It's widely used by many, many organizations, ourselves included, and it is an amazingly successful project. When you consider that the OpenSSL was started by one guy effectively, and then taken on by a group of volunteers, to have gotten to the point where essentially they delivered cryptography to the world. Like lots of organizations, Amazon included, have used OpenSSL for very long periods of time to secure data transfer, to secure things like credit cards being used to make purchases. I don't know of a more successful example of something that's been started from such a small base as a volunteer effort that achieved such great amounts of adoption and made so many things better for the world, right? To have gotten to the point where it's a de facto standard implementation, and literally everybody is using it to secure the internet is just amazing. So I don't want anything that I'm about to go through in Heartbleed to mean or imply that we don't respect that. The OpenSSL project is an amazing, stunning success, and has some issues like all projects do. But it was not, our motivation in initial motivations in coming along with s2n were not about saying OpenSSL is a total write-off, or that it's something we just could never build on top of. It's something we still continue to use. But we had existing kind of plans to build our own TLS SSL implementation, mainly for performance and efficiency reasons, because we realize now we operate at a scale where there are benefits to be had, and we kind of accelerated those when Heartbleed came along. because we thought that would generate a lot of security focus on OpenSSL, and a lot of other issues might come along. We moved things along. So I'll talk about that in a bit. So, the other big motivation, right? It's hard not to it's hard not to cover this for why we started s2n when we did, is Heartbleed, right? So Heartbleed was a security vulnerability that came along in the OpenSSL project on April 7th, 2014. And it was like nothing that we'd really experienced before. You know, we've been through many security vulnerabilities in open source software and have a pretty thorough vulnerability management process in place. But there were a few things about Heartbleed that made it unusual and made it a really good example of how simple vulnerabilities can be, but also how widespread and impactful they can be. To give you a demonstration of just how impactful it was, I have the Google Trends graphs from news stories around the time. The red line is Heartbleed, right? So it was this really big news event when it happened, impacted pretty much everybody. It was on the front page of the New York Times, front page of the Washington Post, front page of probably every major newspaper. Just for context, I chose a long-running news event to provide kind of a context for just how big it was. The blue line is the Iraq War, and it, at its peak, made more headlines on more front pages than even something as large as that, which is huge. I think in general that's a good thing. The fact that Heartbleed made the news like that meant people took it much more seriously, upgraded much more quickly, and so on. But we'd never seen, and since have not seen, any vulnerabilities or security events that were as widely reported or as big a deal as that. And so let's dig into why, right? So if you're not familiar with SSL and TLS, other than that maybe they're used to encrypt traffic on the internet, it's worth understanding a little bit about them to understand the Heartbleed bug. The SSL protocol was invented by Netscape back in 1996, I think, and just stands for Secure Sockets Layer, and then was later kind of taken over and standardized by the IETF, and then it became TLS, Transport Layer Security, but they're effectively the same protocol. But they exist as this layer of cryptography that exists between the low-level protocols on the internet, like TCP/IP, and the higher-level application protocols like HTTP, which is the protocol used on the web, or SMTP, the protocol used for email. And they're pretty pervasive. So every time you go to a HTTPS website, that's SSL and TLS under the hood. So to understand TLS, or to understand Heartbleed, we need to understand just a little bit about how this looks on the wire, like what's actually happening at the packet level. We're not going to get into the cryptographic details of SSL and TLS, but all we need to understand is that on the wire, at the packet level, everything's encapsulated in a record layer protocol that's just part of the TLS standard. And it looks like this. It's really, really simple. There's a message type, and there's a few valid message types. Things like, this is a handshake message, part of how a connection is established, or things like, this is data, this is what your browser is looking for. A protocol version, which just lets us discern between multiple versions of the protocol at the same time. So if you're using SSL, this is a different number than if it's TLS 1.0 or TLS 1.1. Then the length of the record, and then data, right? And when it's a handshake message, it might be data used to establish the connection, and later on in the connection, it's just regular data that your web server is sending to your web browser. Really, really simple. And so there's an extension to TLS called the Heartbeat extension, standardized in RFC 6520. And what that does is it adds kind of another message type that's encapsulated in the record layer, and that message type has its own internal format. You can see it here. And what heartbeats are they're kind of like pings for TLS, right? So either side of a TLS connection can send a heartbeat request to the other end, and the other end is supposed to reply. And the reason this was invented, and the main reason it was designed for is to keep DTLS, which is the version of TLS that runs over UDP, connections alive, right? So firewalls often expire idle connections, and we need to do tricks to keep them alive, and TLS's extension for that is the Heartbleed extension. And so the way it works is, the client just periodically says, okay, send me a heartbeat, and the server sends back a heartbeat. As simple as that. For UDP protocols like DTLS, there's also another interesting property, which is there's a property of the internet called the MTU, the maximum transmission unit, or how much data you can actually send between you and a peer. TCP has mechanisms to discover that. UDP doesn't quite have the same mechanisms, so you have to build it into your application layers. And so it's important for the client to be able to say, okay, I need to find out how much data I can actually transmit between you and I, the server and me. So it might send, okay, I'm going to send you a 1,500 byte heartbeat message, and if that got there, I want you to reply with a 1,500 byte heartbeat reply, and that's how I know I can transmit 1,500 bytes between the two ends, right? And if it doesn't work the first time, it might reduce the number, and then it'll eventually find the number that works in both directions. And that's kind of the purpose of the Heartbleed extension. If the Heartbleed event made such big news, it actually got its own XKCD comic, which is pretty cool. But Randall has a pretty simple illustration of this. We're essentially asking somebody to send us back some data that we sent them, right? So in this case, we send 6 letters, potato, and ask it to reply with 6 letters. And so what the Heartbleed bug was, these are just the numbers that correspond to things. So if we actually use a real example, ignore the first few numbers. Those are just the literal values for each of those things, like 24 is the message type extension for heartbeat messages. But here we're sending a payload length of 3. That's the important number to pay attention to. So that's the client saying, I'm sending you 3 bytes, send me back 3 bytes. And what happened in Heartbleed was that we could change that number to anything we want, right? So instead of sending it, so we'd only send 3 bytes, but we'd ask the server to send back up to 64K, much, much more data. Right? And that's kind of semantically invalid. That's not something that should be allowed. That's not something a server should honor. But the bug in Heartbleed essentially was that it did. So we only sent 3 bytes in my example, but we asked for up to 64K back. And so what OpenSSL would do is it would actually just read 64K, up to 64K of whatever was in memory and send it back, which is an example of a memory disclosure bug. So it's not quite the most severe kind of security bug you can have. That would be something like remote execution, right? Like I can run arbitrary code on the server, but it's still pretty bad. And what made Heartbleed such high impact is this was really, really easy to exploit. Like people knocked up clients within minutes of the vulnerability going public, and they could hit servers, and the servers would reply with up to 64K at a time of data that just happened to be in memory. OpenSSL also didn't do a great job of scrubbing memory or erasing things when it was done with them. So there would be lots of things sitting there in memory, like passwords or sensitive data, including the keys used for SSL connections. And so people had to go revoke and replace all of their keys and so on. So if we go actually look at the code, right, just to see how this arose, it's kind of scarily simple, right? This is code from the actual OpenSSL file that the Heartbleed bug was present in. And essentially what was happening is OpenSSL is parsing the message that it got from the client. If you don't understand C code, don't worry too much, but what we're doing here is pointer arithmetic. So it's taking a raw piece of memory and doing its own arithmetic on that memory to figure out what the size of data the client asked for. And then it just didn't have any check enforcing that matched or was within the record size. And then it just copied that amount of memory and sent it right back to the client. As simple as that. This bug ended up being about 2 lines to fix. So you can consider it a 2-line bug, if you will. And yet generated an enormous amount of impact, which is kind of scary. But there's some stuff going on that kind of created initial conditions to make bugs like this a bit more likely. And so to demonstrate that, so this is the file that those lines of code were in, right? It's called s3_server.c, which just means the code file in OpenSSL that handles the server side of things. If I play this video, so while I'm talking, this is going to scroll through the whole file. It's going to take about a minute. This file is many, many thousands of lines long. You'll notice that it gets pretty deeply nested at points. There's a lot of these blue if-def things going by. There's a lot of hash defines and a lot of different modes of operation that we're going through. The core logic of this code file is a gigantic switch statement that itself is about 2,000 lines long. So switch statement is just this kind of statement that lets us go through different branches of execution or take different paths depending on different things. It is very, very difficult to follow what is going on in this file. So I've been working on OpenSSL for about 14 years now. I've been patching it occasionally and maintaining it, and I consider myself pretty familiar with the OpenSSL code base. A lot of my friends or a lot of core contributors to the OpenSSL project are friends of mine, and none of us could understand that entire file. It's just, there's too much going on in one place. So although we have a 2-line bug that crept in and caused Heartbleed, it's in the middle of so many lines of code that it's kind of inevitable that would happen. It's just really, really hard to catch with things like code review, right? Because you just can't keep the entire context of what's going on in your head. And there were some other contributing factors, right? In addition to the code being just super hard to read and super hard to follow, there were no good test cases, right? So really simple, standard set of boundary test cases, right? Like, so let's just test the boundary values for Heartbleed messages would have prevented this kind of issue, but there were none. So that didn't help. The code, as we saw, right, is just doing raw pointer arithmetic on memory to figure out what a size should be. That's not a great idea. Pointer arithmetic is hard at the best of times. It would be better to just write that once in some place and constantly reuse a function rather than ask it to be done thousands of times in the code. As we saw, it's a lot of code in one file, and I would say with a high cognitive load, right? There's just too much going on to follow, too many branches of execution, too many things for me to track in my mind to be able to really understand it. And then probably one of the more egregious problems is that the Heartbleed function itself turns out just not to even be necessary for like 99.999% of the time. Like the vast majority of TLS usage happens over TCP. It's for regular things like HTTPS and email. They just don't need Heartbleed. That's for UDP protocols. But it was included and enabled by default, even though it just wasn't needed for those modes. And so the combination of all those factors and a really, really simple 2-line bug leads to a pretty massive level of impact, which, for me as a software developer is kind of scary, right? Like, because the notion that, if I screw up 2 lines, I could cause an event as large as this, that, you'd lose sleep overnight. Right? You wouldn't be able to sleep. And so a lot of the rest of this talk is about how we kind of try to prevent those things more systematically, and so that it's not just that, if we miss 2 lines of code, the world's going to end or anything like that. We try to keep things more simple. So our initial response to the Heartbleed event was, so the vulnerability went public before it was intended to be disclosed. There were embargoes in place, and people were working on updating stuff, but for various reasons, the vulnerability ended up going public before those embargoes had expired, and so the world was just caught by surprise by this vulnerability in the middle of a morning. We at Amazon treated it like a pretty major event, as did our customers. You know, we had conference calls spun up, and we were coordinating our response across the company. You know, the first thing we did is halt all deployments of anything, and you know, get everything prepared, because we knew we were now going to have to make a bunch of changes rapidly, and so we wanted to minimize risk for customers. And then we commenced. You know, we actually produced a very minimal patch, with this very smallest change we thought we needed to patch against the vulnerability without importing any other new code that could be additional risk, and started getting that out there super quick, going through our tests and pipelines and so on as quickly as we could. And we got all the AWS services updated within 16 hours, and the vast majority even more quickly than that, without additional customer impact, which is hard. Upgrading, you know, all of something like ELB or CloudFront in those kind of timeframes is a challenge, and a lot of people put in a lot of hours and kind of dropped everything, and it was pretty amazing, as did a lot of our customers. It was such a widely impactful event that we knew would impact many customers, that we kind of went beyond the standard AWS security shared responsibility model, where, you know, we own the security of our services and customers own the security of everything running on their instances or their own software. And we actually put in additional monitoring to connect to customer instances and let them know if they were still vulnerable to Heartbleed, so we would have proactive scans running. And customers did a really, really great job of upgrading. It was amazingly fast. You know, within 5 days, we saw that pretty much 80% of everything had been updated, which is quick. And within a month, 98%. And then if you tracked it like out from there, even a year later, it was like 99% and so on. So the remainder were things people just weren't paying attention to. No one's reading email. No one's monitoring anything. And those type of environments eventually get shut down. But what I think all that means is that the news and the coverage worked, right? The general response, people knew to take it seriously and did, and that was pretty amazing. So that's just stuff on the immediate response and the day itself. More strategically, kind of out of Heartbleed came the Core Infrastructure Initiative, which we are a member of, which is initiative of industry partners that essentially fund research and improvements into projects like OpenSSL to try to improve the baseline security. A lot of new research into vulnerability detection got kicked off as well. My colleague Byron Cook spoke earlier this week about some of that we're doing at Amazon as well, and some of the industry research that's out there. There's been some amazing progresses in the last 2 years, where there's now a lot more automated finding of vulnerabilities. I'll talk about that later. That's really, really cool. The folks from OpenBSD created a fork of OpenSSL. They just copied the code, and then they started immediately ripping things out and simplifying it. And that's the LibreSSL project, which is pretty neat, and it's worth looking at. The Boring SSL project began at Google, which is their own clone or fork of OpenSSL, where they are adding new functionality, some performance improvements, but mainly focused on security and simplifying things down and making it more rigorous. Two really, really cool projects. As I said earlier, we had tentative plans already. It was already on our kind of internal roadmaps, not necessarily a customer-facing feature, but we had already been planning, okay, we're getting to the scale now where, you know, we find ourselves dealing a lot in the nitty-gritty of SSL and TLS. There's performance and efficiency gains to be had there. We should probably get into the business of building our own implementations, right? And so that just suddenly came forward. So there's two kind of common models for open source at AWS. One is it's an official like company project, like the SDKs that we release or blocks. It's a fully Amazon branded project, something we stand behind. And there's also just initiatives where people work on things in their spare time, because that's what they work on. When I joined the company, I was an active contributor to Apache HTTPD. It's just something I worked on for a long time and helped build. And I would continue to do that in my spare time. And so at the very beginning, it wasn't clear like which of these models we would take or I would take. Just speaking personally, not only did I want the new SSL TLS implementation for Amazon, but I also wanted something I could use in Apache. So the initial start was not to worry about that. We'll figure that out later. Just start writing code. And so I started working on it as a spare time project. And to give an example of, or to give you an idea of how complex SSL TLS is, it's not that big. I was able to get a working implementation together in about 40 development hours over about 5 weekends. And I wasn't working on it. It wasn't like I was spending my whole weekend on it. I was just kind of tinkering. And it wasn't too hard. It's not that big a protocol, right? OpenSSL is a huge project, over 500,000 lines of code. It includes every sort of cryptographic algorithm you can imagine and all sorts of cool stuff. But if you really pare it down and you focus on just SSL and TLS, it doesn't take that much to get that working, right? We've done implementations of DNS and HTTP before. In my opinion, those are much, much larger protocols that would take far longer to implement. So 5 weekends in, we've got a working implementation. A lot of that time wasn't even spent necessarily on like writing lines of code so much as just bashing your head off a desk because you're dealing with cryptographic code, and that can be very hard to debug and slows you down a bit. So made pretty good progress. So that's a pretty good kind of initial take. It's like, okay, we could do this. This is totally viable. We could just build this, see what it takes. And so people knew about this internally at AWS, and the feeling was, okay, that looks like something we should take on and do as an official project. And fund it and have software developers working on this for full time and see what that would take, right? So the way we went about that is we wrote up a proposal to make s2n an official AWS project. We use a working backwards process at AWS, which just means we write the press release and FAQ first, and to kind of give you an idea of what it would look like if we launch something. And if people get excited by that, that's generally a good sign. And we went through that with customers. Our feedback from customers was, this sounds great. We kind of trust you to do this. You probably have the technical know-how to be able to pull something like this off. There's an adage that no one should ever really write their own cryptography, which is mostly true, but somebody does have to write it. And we're probably in the small category of places that are in the should. So we kind of crossed that threshold with customers, but literally to a person, all of them said, great, but we want it to be open source. We want to be able to see the code. We want to be able to validate it. We want to be able to trust it, and so on. So that was great feedback. Our feedback from AWS leadership was, yeah, this looks great. This looks like something we could do. But we want to be able to define like long-term ownership, just like a product or a service at AWS. Who's going to own this? Who's going to respond to security issues? Who's going to make sure that it can keep going, that we can survive, the loss of any one individual or anything like that? That we've got a buzz factor of 0. All super important considerations. And so we had to be able to address all of those. The path to open source was surprisingly very, very easy. We have an open source team at Amazon. They work with Amazon Legal, and they were all over it. They were like, yep, if we've got support from the executives, this is no problem. Happy to have it open sourced. probably more complicated than having to deal with any open source licensing issues. We're dealing with crypto export regulations, because when you're writing cryptographic software, you have to have export licenses and so on. But they were super helpful with that too. No problems. We were able to get all that in place. The path to ownership was a little unusual. Normally ownership at Amazon means we have a team of people who work on a service, they own that service. It's very, very simple. For s2n, we actually have a V team made up of people from multiple services. That's consolidating a bit now. It's gravitating towards ownership in one team. But for the last 2 years or so, it's been a V team. But we were able to define who that V team is, who the technical leaders are, what our roadmap is, how we would work with customers. We have an on-call rotation, so if we ever have any issues or urgent problems, we can be paged. And we have a security process that we put in place where we worked with our Chief Information Security Officer, Steve, and Andy Jassy, our CEO, to just define exactly how we respond to issues. Of particular concern is, customers are going to be using this software as well in some cases since it's open source. So what our notification process is, how would we notify them in the event of a security issue? We have all that well defined. If you go to our GitHub project, you can see what our notification process is, how we handle them. There's an email list to sign up to if you want to be notified of issues and so on. So those were kind of the processy things we had to do. And they weren't particularly large roadblocks or anything like that. They were just a matter of addressing them and documenting them. And then we were able to launch. But before we were able to launch, we had to build the rest of it, right? So in those 5 weekends, I built enough to be able to, connect a web browser to a web server and download some stuff. But to really, really work at scale and deal with, millions of different client types, there's a lot of long tail work of compatibility testing and efficiency and performance testing and so on. And so we had to get the V team spun up and define how are we going to own and develop this project going forward? What was that going to look like? So that's what I'm going to talk about next. And so I've split this into what I think are the 5 levels we really think about this, at least how I learned to think about it, working in AWS. And those are to focus on the team culture, just how we own something as a team. And then in much more practical terms, how we come up with simple designs and focus on readable code to make things maintainable. Quick and easy testing, systematic defense in depth, and verifying everything. Verifying everything is probably a unique aspect to a project like this that's super security focused. But we'll cover that too. So when we started the V team, we did something that we do with most service and product teams at Amazon, which was we actually agree and write down what are our goals, priorities, and tenets. We call them tenets at Amazon, but we call them development principles on our GitHub project because we got feedback from a lot of international developers that they didn't know what the word tenet meant. It's not that common an English word, and that helps keep everybody faced in the same direction. The way I think about it is we always try to make data-driven decisions, and whenever there's an argument that can be resolved by data, it should, but there's always some amount of decisions left over where you kind of have to go back to some guiding principles. And so we write them all down and hash them out in advance so that we can all be lined up. We also agree and write out our actual code guidelines, what our code should look like. One of our core tenets and principles and thing we probably spent the most time on was just making tests super easy to write and super fast to run. Really, really important thing to get right from day one. That's usually where we focus a lot of energy when we start things. One of the ways we think about that is if we take testing under the umbrella of quality, a lot of time people can have the impression that quality is something you should make time for, or that it has to be accounted for in development budgets and so on. We'll set time aside to do the testing, and we'll. But we don't think about it quite like that. Instead, think of it as a habit that has to be constantly reinforced as just part of how we do everything. It's more like brushing your teeth. than anything else. And so in that context, like we had to start by saying, well, what are tests going to look like? How are we going to make them really easy? And we thought hard about the high-level design. Our actual goals, once we wrote them down, came out to be like this. Let's write a world-class TLS implementation. Let's stay minimal. You can read all of our goals on our website. Actually, if you go to the GitHub project, you can read all of this. We've got a pretty long document that goes through like what our development principles are in fine detail, what our coding guidelines are in fine detail, and how we think about resolving decisions. It's all there. Take the time to read it if you're interested. So that's at the cultural level, right? That's how we stay kind of generous and healthy as a team and reinforce each other to do the right things. But we also need like just super practical day-to-day guidance for doing certain things. And of which I think the most important is how we write code. You know, we're software developers. What we're doing every day is literally writing code. We need to think hard about it. The biggest thing we optimize for, in s2n for sure, is that the code be readable, right? It needs to be understood not just by the compiler, but by our colleagues, by people reviewing it, especially since this code base is going to be reviewed so thoroughly, and by our future selves, who may have forgotten a lot of the internal details from when they wrote it. You know, one of our really simple guidelines for that is the code itself should be super readable in terms of what it's doing, right? Like functions should have easy to understand names. The code should have this simple flow to it. Like I should be able to just read a function and be able to tell you what it's doing. If I'm writing comments explaining what I'm doing, that's a bad sign. Like I probably need to rewrite the code or restructure it to be more readable. But we do encourage verbose commenting to explain why we're doing things, right? So if I need context from outside the code, like referencing a standard or some other part of the code base that's too far away to keep in context, like that's a why, and those are worth commenting. And that rule's never let us down. None of us on the V team particularly like to argue about how code should be formatted, you know, spaces and tabs or any of that stuff. So we just took a hint from Go and automated it all from day one. So we have a make target in our project that will consistently indent the entire project. And we encourage everybody to just run that command every single time. And we've never, ever had an argument about code formatting. And if anybody wants to change anything, they can. So just a really simple example of some of our code. This is a piece of code that actually handles a TLS extension. And what you can see, we've got some why comments, right? Like they're there to explain why things are the way they are. But the functions themselves should be pretty readable in terms of what they're doing, right? So like I'm writing a uint16, right? It's telling me, okay, I'm writing an int, it's 16 bits in size, really, really simple. All the context is there. And that's kind of our ideal. Just make it at least that readable. So we prioritize readable code above anything else, right? If we have to make code bigger to make it more readable, we will, right? That is our highest priority. But in general, we also value less code over more code, right? So if we can make the system use less code to do the same thing, that will generally have fewer bugs. You know, defect rates are generally measured per line. And it will just be easier to audit overall. That initial version of s2n that I wrote, that it could connect a web browser to a web server, ended up being about 3,000 lines of code total, compared to about 150 to 200,000 lines of OpenSSL code to do the same work, out of OpenSSL's total of about 500,000. We explicitly try to avoid branches as much as possible. So like just ifs and switches and so on. We try to eliminate them because they put a really high cognitive load on the developer, because now you got to keep context of like, well, if I go here, what happens? And then that can get into a combinatorial space, right, when you end up with lots of them. We try to write small, simple, discrete functions that do one thing, just so that I can sit and read a function in isolation and not have to keep a ton of context in my head. Again, really optimizing for like our own brain spaces and readability. Since we're a networking library, Another great trick we applied is we intentionally split the parsing of messages, like handling things like the Heartbleed extension, from flow control, which just means like, well, where should I go next, managing state machines, all that kind of stuff. It's just so the code isn't all mixed together. A simple example of that is kind of the high-level design of s2n, is that we take input, we parse it to a function that decrypts things, we parse it to another function that parses or responds with that data, we parse it to another function that can encrypt a response, and then we send output, right? Which is pretty different to, say, the OpenSSL style, where it's that one big file doing everything at once, all in one big context with a switch statement at its core, is that it's trying to do everything. We're trying to make these discrete units of operation. One trick that we use to avoid branches is that a lot of the time, the functions that we're going to are referenced via function pointers. So we just plug different functions in the same place in like a modular framework. It's just kind of like a functioning programming technique, just to keep things down. And so if you look at a typical, like how a message is parsed in s2n, it's very, very different from that OpenSSL code that we saw earlier, right? So this is us handling a particular message in TLS, which is the change cipher suite message from a TLS client, doesn't really matter. But what we do is, this is the whole file, pretty much, and we've got the code for receiving a message right up there on top, and the code for sending it right there at the bottom. And so that's how we're oriented. We're like, this is the file you need to read if you're reviewing how we handle this message. So you've got all so in your brain, you can be like, okay, at this point, all I need to really understand is the format of that message. You should also be able to understand that format just by reading this code, really, right? If you look at the bottom function, you can see all that's happening in that message is that we're sending an 8-bit integer that is, in fact, the entire contents of that message type. It takes a little bit more to receive that data because we have to set up some state based on when we receive it, but it's really, really simple. All the functions are hopefully pretty legibly named, pretty easy to follow. So I mentioned branches. So you'll notice we're not deeply nesting here in branches. We're not getting deep at all. It all fits on one page. That's all intentional. I want to go back to the file we looked at earlier from OpenSSL. So this is just one section from like somewhere in the middle. What you see here is kind of like a kind of beginner novice programmer error, which is nesting lots of branches deeply. And because it's got the mindset, okay, I need to check if some condition is good, right? Like this one at the top, we're checking if G is not null. Because if G is null, we can't do anything, right? So G has to not be null. So I'm going to check that. And then I also need to care if like ctx.g is not null. So I'm going to do that next. And so on, right? And you get many nested branches deep, which is a lot of context to keep in your head. And also just makes the code like really hard to read, right? It ends up looking like this. The branches keep going to the right. And it literally falls off the screen at some point. If you trace the maximum branch depth in OpenSSL, it gets sometimes 32 branches deep, which is just a lot of context to keep in your head, right? So in s2n and in general, coding guidelines, we do it the other way around, right? What we'll do is, like if a condition is not what we want it to be, bail, right? Exit. So what we would do in that case, we would say, well, if G equals null, return -1. Done. I can forget about all that context now, right? And instead of having these nested series of branches, you end up with like just this straight line of code that's really easy to read. And it's much harder for errors to keep in. So this is like just a really simple trick to, especially for beginner programmers. Like if you can get into that habit early, it is well worth having, and it'll generally make all your code smaller and simpler. Anyway, that's just one example of like our explicit coding guidelines. If you go through the reference doc on GitHub, you'll find more. So as I mentioned, we think testing is pretty key. You know, I am not the kind of software developer that can just, you know, Frank Zappa style, like write the best code in the world the first time that, you know, it's flawless. I generally make a lot of errors as I'm coding and catch them with tests and then iterate and fix, right? And and I want to make that development cycle as quick as possible. And so we put a lot of focus on that from day one. One of our explicit testing guidelines was that tests should be so easy to write, there's no excuse not to have a test, right? Tests need to be easy enough to write for interns, because we have interns working on our project sometimes. And to reinforce that habit as well. And they should run quickly, right? Because it's just a nuisance if they don't. It slows us down. So we did that. We have a lot of tests in s2n, a lot. If you go download the project from GitHub and type make, or do make-j32, which will just parallelize everything, we run through literally billions of test cases in the test suite, and it all finishes in less than about 20 seconds. On my Mac at the moment, they finish in 8 seconds. So I can be writing code, I can be adding new tests. I'll do make-j. 20 seconds later, I know if all my tests pass or fail. s2n is written in C for backwards compatibility reasons. We were replacing OpenSSL. OpenSSL is written in C, so we kind of had to write it in C. There's a lot of religious wars about whether C is right or not for security-critical software like this. All I'll say is when you're replacing a C project, you pretty much have to use a C project to replace it. And also in crypto, there's some times where you need constant time code, and you can really only do that in C. Anyway, that's an aside to all this. But C doesn't have a test framework, right? There's no JUnit for C. Well, there's a few competing ones, but no clear leader, no idiomatic testing framework for C. So you have to write our own. It turns out that's not that hard. We wrote our own testing framework in 11 lines of C preprocessor include macros. You can go see them in the GitHub repository. And we made it this easy to write tests, right? So it's very JUnit-like in structure, where essentially we define little programs that are the test cases, and the tester can do whatever they want in those test cases, and we're done. Really, really simple. And that's how we have many test cases. And those turned out to be amazingly fruitful when it came to verifying things, because all those test cases could be used in verification software as well. If we go back to this example a little, you'll see when we're writing and parsing messages, I didn't mention it the first time, but we're not doing that direct pointer manipulation that you saw in OpenSSL, right? We're using these stuffer functions instead to write integers. And that's an example of how we do systematic defense in depth in s2n, right? We don't want to just rely on programmers not making errors everywhere. We want to have procedures that would defend against many types of error recurring. So the kind of first level that we do of that is just really simple safety stuff. So we turn on basically every C compiler warning you can imagine, everything we can find, we turn them all on. We do that by default every time we compile. So lots of as much paranoia as we can do there. We have a lot of built-in safety routines that we encourage liberal use of, sprinkled throughout the code base. So we have safe versions of memcopy, for example, checking that returns are what they are. We have safety routines for checking that things are null and not null. These are also really useful when debugging, because you can kind of redefine a macro and put a printf in there if you want, and see where you're triggering an error. And the stuffer is another example of that, right? So I/O is so common in a networking library that we decided, okay, we would build in first-class support for that. So instead of doing typical C style, like OpenSSL was, just raw buffer manipulation with pointers, we're going to emulate something like Java's byte buffer class, where we're going to use streams, right? We're going to have, so that's what a stuffer is. Stuffer is a buffer for stuff, or a streaming buffer, depending on what way you want to define it. But it's just a really simple C structure that has 4 pointers, a pointer to the start of a memory region, the end of a memory region. It's got a read cursor and a write cursor so that we can write and read into this buffer in a stream style. And it's got some really simple functions to tell you how much space is left, how much data is actually in there. And then we construct all I/O, all serialization, all marshalling and demarshalling as just operations on that stuffer. So I can read ints into it, I can write ints from it. It enforces very simple guarantees, like, well, I can't read past the end of a stuffer, right? So that's like a defense in depth directly against Heartbleed, right? Just couldn't happen. Stuffer wouldn't let it. Like, we would try to read 64K. So let's say we made that error, right? Let's say we didn't have a check for 64K. Well, we try to read it from the stuffer. The stuffer like, well, I don't have 64K. You can't have it, right? So now we've got defense in depth, which is pretty awesome. Our stuffer also has routines for like turning things to hex or from hex, doing all sorts of useful things. We use it in other projects. It makes things far, far simpler, deduplicates a lot of our code, right? Really, really cool. You can do some, if you look at this one, I've got like a raw read routine into a stuffer, which basically lets me say, you know, I'm going to get TLS finished len amount of bytes from the stuffer, so make sure it's there, you know, can't read past the end. And then I've got another safety routine, and this one actually constant time equals, because I'm doing some checking of that memory, whether it is what it should be, and we need to do it in a secure way, not leak any data. All these are examples of what we've built in, and if you go look at the s2n library, you'll find, you know, many, many more examples. But that's the kind of defense in depth we play. So this is how I sleep at night, right? Because if I miss the easy to miss detail of, oh, I forgot to check about whether it's 64K, we have layers of defense that will catch those. And then below this again, wait, we want even more defense in depth, right? So we want to actually try to formally verify that we don't have bugs. So before we launched s2n, we had done 4 like full code audits. Basically, we had done 2 government ones and 2 commercial ones where we provided them with the entire source code, and they basically read through it, did their own testing, tried to find any defects. Before we launched, they had found 4 defects, all of which are documented and included in our commit history. You'll find them if you want to find them. The most serious of which was a small memory leak in an error case. So the client could send us malformed traffic, and we would leak 4 bytes of memory each time. And so if the client did it enough times, we'd eventually exhaust memory and give up. And that was the most serious vulnerability we found. So that was encouraging that that's not too severe. But we also we've done more audits since, 2 more since, that's why it's 6. And anything we ever find, we always put it in our GitHub issue tracker. But we started doing more formal verification, right, using mathematical techniques to actually find issues. We have been working with a company called Galois and another company called Trail of Bits on doing formal verification of our HMAC code, which is just a cryptographic algorithm we use. We've got automated fuzz testing now of everything. So on every single commit, we are now doing both formal verification of our code and fuzz testing of all the code. And we're working on automatically identifying side channels, like going beyond what we just want to read into them. If you're curious about any of these, you can go look at them. The SAW tests that we have in s2n is a really good thing to look at. Those are the contributions from Galois that cover how we formally prove that our cryptographic implementations are correct. You can look at Byron Cook's talk from earlier this week. It'll be on YouTube. He goes into much, much more detail about what they're doing here. He's from the Automated Reasoning Group, which is where I got this cool t-shirt. From all that, where are we today? So s2n, when we started it, you know, we're Amazon Web Services. We're very server-side focused in general. We're still very focused on that. So s2n is not a general purpose replacement for OpenSSL. It includes hardly any client support at all. We're just beginning on that net because we do have plans to include it in spaces like IoT and so on where the client is more relevant. But up until now, we've generally been focused on writing a server implementation because that's what we know best. It intentionally doesn't have support for a lot of features. Like, it doesn't support the Heartbleed extension. That's an intentional security choice. A big missing one that does hold people back from using us is we don't support client certificate authentication at all. But we're working on that right now. We were writing code earlier this week. So that's coming pretty soon. We've been turning off support for insecure things. So since we launched s2n, the world decided SSL v3 wasn't safe anymore. 3DES isn't safe anymore. So those are now all turned off. We've got 7 active contributors at Amazon, and our bus factor is 0, which just means like any one of us could leave or have a terrible accident falling in front of a bus, and the project will be fine. There's sufficient leadership there to continue. Everything's well documented, and it's all pretty stable. We've had contributions from 11 non-Amazonians, so I'd say s2n is an example of an open source project that's, it's kind of small, it's a niche area, it's never going to be the kind of project that's going to have a lot of external contributions. Like the amount of people in the world just randomly interested in working on hardcore crypto in their spare time is not that large. So I think we're doing pretty well there. We are using it in production. It's in front of like AWS traffic right now. Not everything, and an increasing proportion over time, but it's there. Without us really focusing on performance improvements yet, we think we have significant room for improvement there. We've identified some cool things we think we can do. We're seeing about a 2.5% performance improvement in terms of throughput over OpenSSL. The main reason that is we just go through so much less code effectively. To go through a few thousand lines of code instead of going through tens and thousands of lines of code is where that comes from. It's pretty cool. I'd say our key takeaways, like the things I would most want to sell anybody on from the project, that most benefited us, and I would repeat every time starting a new project, is that act of writing down our goals and our development principles and our code guidelines has been so beneficial in onboarding new people. Like, we get code contributions from people we've never met or ever even spoke to, and they are matching the decisions we would make because we took the time to write those things down, which I think is amazing. Just a huge productivity boost. Writing readable code, even now, I think that, 2 years ago, when we started the project, we focused on readability because I've already forgotten a lot of those internal details. But it's readable enough that I can get up to speed very quickly again. I don't have to spend hours going like, what does this do? Making the testing habitual, I think, has probably been our biggest payoff of all, especially because that made the formal verification easier. We had external contributors come along. We had a great company called s2n, who were funded through the Core Infrastructure Initiative, come along and verify that s2n had no undefined behaviors in its code base. Well, they actually found a few cases, which we fixed, and now it has now undefined behaviors in the code base. And they were able to do that because we had all the tests. Like, they were able to use the test cases as a mechanism to find all those, which is pretty awesome. So I'd say that's worth repeating. Thank you all for coming. Fill in your evaluations if you remember. This is NET405. And if you get a chance, I definitely recommend both Byron Cook's presentation from earlier this week. If you weren't there in person, go watch it on YouTube when it gets up. He talks about formal verification at length. It's great. And Eric Banwine's talk about encryption, which will be super interesting to this audience, I think. Thank you all.